Tonight, gravity should win. A storm rolls over a small tree in the darkness. Rain lashes through the branches. Wind bends the thin twigs back and forth. Lightning flashes behind a tiny songbird sleeping above the forest floor. Its eyes are closed. Its body is still. The branch moves violently beneath it. And yet, the bird does not fall. Its toes stay wrapped around the bark. Its feathers ripple in the rain. Its chest rises slowly with each breath. This looks impossible. If a human tried to sleep on a narrow branch, the body would relax. The grip would fail, and gravity would win in seconds. But birds are not simply holding on. Their bodies contain a mechanical lock, a secret system hidden in the legs and feet that allows them to sleep above empty air. This is the world of the gravity defiers. The answer begins in the tendons. Inside the bird's leg, long flexor tendons run down toward the toes. When the bird lowers its body onto a perch, its leg joints bend. As the joints fold, the tendons tighten automatically. The toes curl inward. The branch becomes trapped inside the foot. The body's own weight activates the grip. No conscious effort is required. No constant muscle tension is needed. The deeper the bird relaxes into its sleeping posture, the tighter the toes can hold. It is nature's deadbolt. Weight pulls down. The tendon pulls closed. The branch pushes back. The toes become a clamp. Relaxation does not weaken the grip. Relaxation helps engage it. That is the first miracle. A sleeping bird is not fighting gravity with effort. It is using gravity to lock itself in place. To leave the branch, the bird must straighten its legs. When it rises, the tendon system releases. The toes open. The deadbolt unlocks. Then the bird launches into the morning light. Flight opens the lock. Sleep closes it. But grip is only half the story. The second problem is balance. A sleeping body still sways. A branch can move. Wind can push from the side. Rain can shift weight. Even a tiny change in body position can create torque, the twisting force that tries to rotate the bird off the perch. So the bird needs more than locked feet. It needs a balance system. Like humans, birds use the inner ear. The semicircular canals sense head movement, rotation, and acceleration. But birds may also use another extraordinary sensor near the hips, the lumbosacral organ. This region, located near the pelvis, may help birds sense body movement and balance directly. It is as if the bird has another stabilizing system built into the lower body. Head, hips, feet, and tendons work together. The head can stay steady while the branch moves below. The body can make tiny corrections without fully waking. Balance becomes a whole-body circuit. Even while sleeping, posture survives. The bird does not need to think, "I am falling." Its sensors detect small shifts before disaster happens. The body leans back into stability. The feet remain locked. The center of mass stays over the support. Grip handles attachment. Balance handles position. Together, they defeat falling. This is why a storm can shake the branch, and the bird remains asleep. The wind tests the lock again and again. The rain adds weight. The branch whips through the darkness. But the system holds. Almost zero energy. Almost no effort. Mechanical safety in the middle of sleep. Some birds take the challenge even further. In tropical forests, hanging parrots sleep upside down. They cling beneath branches like green fruit hidden among leaves. It looks more like a bat than a bird, but the solution is brilliant. Predators often approach from below. Upside down creates distance. Leaves hide the sleeper. The feet become ceiling hooks. Gravity pulls downward, but the claws answer upward. The bird turns falling into holding. For hanging parrots, strange geometry becomes protection. Other birds sleep on walls. Swifts may cling to vertical stone, chimney shafts, or cave walls. Their feet are built for clinging, not walking like ordinary ground birds. In groups, walls become dormitories. Height becomes safety. A vertical surface becomes a night shelter. At Davn, the wall becomes a runway. The swifts launch into the sky, and the strange night ends in flight. Then come the one-legged sleepers. A flamingo stands in shallow water with one thin leg supporting the entire body. Its head tucks into its feathers. Its reflection ripples beneath it. It looks impossible, but the flamingo is not straining the way we imagine. Its body can align its center of mass over the standing foot. The posture behaves like a support frame. Some research suggests that flamingos may use passive mechanics that allow the body to remain stable with surprisingly little muscle effort. Gravity can help stabilize the stance. The pose is not just balance. It may also conserve heat. Legs can lose warmth quickly, especially in cold water. By tucking one leg into the feathers, the bird protects that limb and reduces heat loss. Stability and warmth work together. A whole flock of flamingos standing on one leg is not just elegance. It is physics in disguise. Storks, herons, and many other wading birds use similar poses. Long legs are useful for walking through water, but they also invite heat loss. So the bird hides one leg, manages blood flow, and lets posture do part of the work. Gravity has been negotiated. Now compare that to human sleep. When humans enter REM sleep, many muscles become temporarily limp. The bed catches the body. We can dream, twitch, and lose muscle tone because we are lying on a flat surface. Birds cannot afford full collapse. A bird sleeping on a branch has no mattress. Its REM sleep episodes are often very brief, sometimes only seconds long. The head may dip slightly, then recover. The body may twitch, then reset. The feet remain locked. The balance system keeps reading. Mechanical grip bridges the risk. Short REM helps prevent long periods of dangerous limpness. Micro-arousals restore control. Then rest continues. Bird sleep is not simple relaxation. It is controlled vulnerability. A branch is not a bed. It is a trigger. Body weight pulls the trigger. The toes close the clamp. A slip can increase tension. The mechanism self-corrects. This is why birds can sleep on branches, wires, ledges, cliffs, walls, reeds, and even one leg in water. Different feet solve different gravity problems. Perchers clamp. Waders distribute weight. Climbers hook. Swimmers float. Flamingos balance on geometry. Hanging birds invert the challenge. Every habitat creates a sleep problem. And anatomy answers. A sleeping sparrow on a wire uses a different solution from a flamingo in a lake. A woodpecker roosting against a tree trunk uses a different solution from a duck floating on water. A pigeon on a city ledge uses a different solution from a swift clinging to a chimney. But the principle is the same. Rest must not become falling. The forest is full of hidden sleepers, each one solving physics silently in the dark. Underneath the peaceful image, the machinery is working. Contact creates friction. Curved toes fit uneven perches. Foot pads increase contact. Tendons maintain tension passively. Balance sensors track sway. Feathers insulate the body. Posture controls torque. And the system saves energy so sleep can focus on recovery. This is why engineers study birds. A passive gripping foot can inspire robotic claws and drones that land on branches without wasting power. A tendon lock can teach machines how to hold position without constant motors. A bird's balance system can inspire better stabilizers and sensors. Nature built it first. The deadbolt was biological. The tendon was a cable. The body carried a gyroscope. The branch became architecture. And sleep became engineering. By morning, the storm fades. The rain stops. The branch still sways. But the tiny bird is still there. Its eyes open. It shakes water from its feathers, and looks down at the forest floor below. The height was never the problem. The design was the answer. Then it straightens its legs. The lock releases. The toes open. And the sleeper becomes flight again. Gravity lost all night. So the next time you see a bird sleeping on a branch, do not see something fragile. See a living machine of tendons, balance, posture, friction, and instinct. No panics. No effort. No falling. Only structure holding against gravity. A tiny tendon defeats the fall. A sleeping body trusts its own design. And somewhere in the night forest, thousands of birds are resting above empty air, quietly proving that biology solved the equation long before we ever asked the question.